Hello GCA candidate, welcome back to School for All. I hope that you are doing well and preparing well for your exams. So our lesson of today will focus on advanced level further maths paper 3 moment of inertia. So this is one of the most challenging topic in paper 3, and I hope that my video of today will really help you for your exam on Saturday. Okay students, so when we talk about moment of inertia, what are you understanding about moment of inertia of a body? Okay, so what you should know here is that moment of inertia of a body is the reluctance of a body. Is the reluctance of a body to rotate. Are we understanding? So moment of inertia is measuring what? The ability of a body to be what? To resist rotation. Are we understanding? Ability of a body to resist rotation. And you people should know that all those that are dreaming to do civil engineering, building, construction, and all those things, this topic is very important for you people. It's okay. And of course, those that are doing further maths, yeah, I think that if you are a student doing further maths, yeah, you should be dreaming to do engineering, all those fields of engineering, civil engineering, mechanical engineering, and all those things. So don't forget to join us on the 30th of June. Those that are very near to Nguso or very near to a source, yeah, if you are close to a source and close to Nguso, we are having two centers there, Collège Polyvalent. We are having Collège Polyvalent at the Santo Nguso. We are having a Collège Mongo Biti at Mobile Source. So if you are near those areas, don't forget to join us on the 30th of June for a great career orientation already. So those dreaming to do civil engineering, all those things, your dream can still be achieved, because there's Polytechnic that is being launched already, Polytechnic Douala, Yaoundé, and Polytechnic Ezeka. So they are being launched already. So join us on the 30th for a great career orientation, so that we should guide you on how some of you can enter prestigious schools and achieve your dreams. So that is it. So you can still contact me for more information. You can still contact me on the in the comment section of the video, or you can still take the number which appears at the level of the screen. It depends on you. So let us continue. As I was saying, moment of inertia is that reluctance of a body to rotate. Is okay. So now the formula. So that was the definition of moment of inertia. So the formula to calculate the moment of inertia of a body, there are two kinds of body. There are bodies which have discrete masses, as I did in what center of mass. Those that watch my video on center of mass, a body made up of discrete amount of masses. So discrete masses is okay. For a body having discrete masses, the moment of inertia denoted as E. For a body have discrete masses, the moment of inertia denoted as I. For francophone, it denoted as what? J. The moment of inertia denoted as I of any axis of rotation is given as the sum of those discrete masses times what? Times the distance separating what? The distance separating the mass and the axis of rotation. Delta here is the axis of rotation. M is the mass of the system, the individual masses of the system. Is the reason why I'm summing it. Then x is the distance from the distance from the axis to the mass, axis of rotation to the mass. Okay. Now for continuous bodies, for a continuous body, this is for a discrete body having masses. The moment of inertia about an axis of rotation. Now, I told you that for continuous bodies, we are now applying what? The integral. For continuous body, we are applying the integral. The integral of x dm. X squared dm. So that is it. Moment of inertia of a continuous body, integral of x squared dm, where m here is what? M is the mass, elementary mass of the continuous body. X is the distance from the mass to the axis of rotation. So those are the two formulas you should note about moment of inertia. So those are the two formulas you should master. Now, it means that if maybe I'm having a body, take note, if I'm having a body considered as a point mass, it's okay. I'm having a body considered as a point mass, and I want to rotate that body maybe about an axis placed at point O, is okay. And the distance from the point mass to point O maybe is d, the moment of inertia of that point mass about the axis O is simply equals to what? The mass, the point mass is having a mass m, times the distance from that mass to who? To the pivot. Is okay? Or to the axis of rotation. The axis of rotation can be an axis passing through O. So that d then what? Square. As simple as that. So this is the moment of inertia about what? This is the moment of inertia of a point mass about a pivot placed at a distance d from the point mass. As simple as that. Okay. This is when I consider a point mass place. Point mass, it means I'm not considering a solid. For a solid, you are supposed to integrate. A solid is made up of what? Continuous masses. So you're supposed to integrate. For a system made up of discrete masses, you're supposed to sum. But for a point mass, this is the formula. Okay, so without wasting time, let us take a small example to better explain what I'm just from. The example here will be, let us calculate. So calculate of a road of negligible cross-sectional area. So calculate the moment of inertia of a road of negligible. There's a small example. I will show you how to calculate the moment of inertia of a rod of negligible thickness. It means that the road, the road, it is like this. Let me put it. It means that the length of the road as compared to the thickness of the road is very what? Small. It means that the length of the road is very big as compared to the thickness of the road. So I neglect the thickness. Okay. Now let us say the road is having a length of 2a and the mass of the road is big M. Is okay. Then this is the center of the road here. If I call this the center, it means that what? Here should be negative A, here should be A. For here to be the center. It means that the axis, I can put my axis here. This is the x-axis. This is the y-axis. So I want to calculate the moment of inertia of this road of length 2a, mass big M, of negligible thickness. Are we together? So for me to calculate the moment of inertia of this, you should first of all consider. It means that if I neglect the cross-sectional area or the thickness, if I neglect the thickness of the road, it becomes a one-dimensional object or a one-dimensional solid. Are we together? And for a one-dimensional solid, we are talking about what? A one-dimensional solid means that what? I will consider one axis. It means I will consider the x-axis here. So I will take this, my formula to calculate the moment of inertia is the integral of x squared dm. Are we together? No. Are we together? Okay, student. Now, I tell you that integral, I'm summing a continuous body, I'm summing. So I would consider a small portion. Let me consider a small portion like this. It's okay. I will consider a small portion of my road. It's okay. Of length, maybe x. Then I will take down that small portion. I will now sum it by using an integral to come out what? The moment of inertia of that road about what? The origin, or about an axis passing through the origin. I hope you are together. Now, if I let the density, is okay, it means that the linear density, why am I talking about linear density? As I said, it's a one-dimensional figure, so it is a linear density. The integral will be what? Along only what? One direction. So the linear density of this small portion of my road will be what? The mass, small mass, m all over the length. Linear density is mass all over length. Mass per unit length. Linear density. One dimension figure. It's having linear density. I'm looking for dm. So from here now, you see that what? I can come out with my m. But to come out with the m, I'm looking for dm. Dm means a small displacement of m, or an elementary mass. Dm, elementary mass. So I will come and make m here the subject. I will have lambda x. Then I will look for dm. To look for dm, I should what? Differentiate. It's okay. Small elementary mass, small displacement of the mass. So it's the meaning of differentiating. So I will differentiate to respect to x. I will have what? Lambda. So this implies my dm is simply equals to lambda d dx. This is my expression of dm. I hope you understand it. As simple as I come up with the expression of dm. So m mass is coming from what? The linear density. Linear density is the mass per unit length. I consider the length of my small portion here to be what? To be x. I consider the length of the small portion to be x. Now making my lambda to be the mass a small mass by the small mass of this portion divided by the length of the portion, which is x. From there now I can come out with my dm. Now having the value of dm, now I'll come and replace here. So the moment of inertia about the center, the moment of inertia of the rod about the center is simply equal to the integral, is okay, from, look at my small portion is starting here from negative a to 0 of what? Of x squared lambda dx plus integral from 0 to a. I should make sure I should take all the rod. So to take all the rod, I should start from negative a to 0, then 0 to a. So from 0 to a of x squared lambda dx. As simple as that. Now you can see that what from negative a to 0, 0 to a, we can also see that it is simply the integral from negative a to a x squared lambda dx. As simple as that. Then from there I integrate. I think everybody here can integrate. I will integrate. I will have lambda x cubed all over 3 from negative a to a. When I replace, I will have lambda all over 3 a cubed minus a cubed. So when I replace, I will have lambda all over 3 into 2, exactly 2a cubed. Okay, but I know that a lambda is simply equals to what? The mass per unit length. Now our lambda here, I want now the mass per unit length of all the rod. The linear density of all the rod will be big M. The big M, that is the mass of all the rods, divided by the length of the rod, which is what? 2a. So this implies the moment of inertia of the rod about its center is simply equals to what? Big M all over is simply equals to big M all over 2a into 2a cubed. Pardon, there was 1/3 here. So 2a cancel here. So I will have 1/3 ma square. As simple as that. Are you seeing that? Nothing to fear here, my students. Nothing to fear. As simple as that, you come up with the moment of inertia of the rod about its center. Formula to cram, procedure to be cram. So sometimes they will ask you, so is the reason why I'm saying that you should cram the procedure. You should understand, you should understand the procedure and cram the formula. Okay. No reason even to cram the formula. You can still understand the formula. Moment of inertia is a mass times the distance square. Now, since it's a continuous body, you are supposed to put now what? Integral. Okay. So that is the moment of inertia of a rod about an axis passing through its center. As I said, linear density is coming from. Why am I using linear density? Is because I'm having a rod of what? One dimension. When we go to figures of 2 dimensions, you see that I will not use linear density. I will not use what we call surface density. Is okay, or area density. Also in French they call it densité surfacique. So surface density. Now here you will not see volumetric. Volumetric density is for space, because space in 3 dimensions. You will not see it. You are not seeing it in the advanced level. That is already a university program. And then you call now it volumetric or volumic density in French. Densité volumique. So that is it. Those that will do Polytech and all those, you will see that. Okay. Now, the next part of our lesson, I want you people to understand is what we call parallel axis theorem, or what we call Eugene theorem. I want us to understand that theorem. Now, if let me put this one here because we use it after 1/3 m a square. Now, if I ask you to find the moment of inertia, still under this question, but I ask you now to find the moment of inertia about one end of the rod. It's okay. So if I ask you to find the moment of inertia about one end, or about an axis passing to one end of the rod, about one end of, let me call this end A and this one big B. If I want to calculate the moment of inertia about one end of the rod, you can still calculate it through what? Integral. But that one is long. There is parallel axis theorem that come and simplify the thing. I will do the 2 method you will see. Now, if I want to use the parallel axis theorem, so, or Eugene theorem, what is parallel axis theorem says? Parallel axis theorem says that if I want to calculate the moment of inertia if I want to calculate the moment of inertia about one n, let's say that this n is A, I want to calculate the moment of inertia about an axis passing through A of this rod. I will first of all calculate the moment of inertia. I will first of all calculate the moment of inertia about an axis passing through the center of the rod. An axis passing through the center of the rod. So if I want to calculate the moment of inertia of an axis passing what? Through one end of the rod, or passing through A, I'll first of all calculate the moment of inertia about the axis passing through the center O, plus I will take the mass of the rod, which is big M, times the perpendicular distance separating the two axes. This is the two axes. So this is the distance separating the two axes. The perpendicular distance separating the two axes. This is it. The axis passing through the origin and the axis passing through one of the end. That perpendicular distance is how many? A. Then I square it. So there is it. That is parallel axis theorem. As easy as that. If I want to calculate the moment of inertia about an axis passing through one of the end of the rod, I first of all calculate the moment of inertia from the center, about an axis passing through the center, plus the mass of the rod times the distance square from the center to the end of the rod, or the distance square separating what? The two parallel axes. As you are seeing, the axes are parallel. One, the axis passing through the origin and the axis passing through one of the end are parallel. You take the distance separating them, and that distance should be what? A, because the distance from here to here is 2A. Therefore, the distance from one end to the center should be A. As simple what? That value will give us okay, the moment of inertia about the center, we calculated it already, is 1/3 ma square plus ma square. Then the formula, the answer will be 4/3 ma square. As simple as that. There's a moment of inertia. Just from calculating the moment of inertia of this rod about an axis passing through the end A of the rod. You can still do it by integrating. You will come now here, the moment of inertia about A will be simply the integral. Now you are integrating. Since it's about one of the end, you will consider what? You consider maybe the origin to be here, and then here should be 2A. You are integrating now from 0 to 2A directly of what? It's the same thing, of x square lambda d dx. As simple as that. When you integrate, you come up with the same answer. Okay, students. So that is it. Students, so the next part of our lesson here, I want us to talk about important laws to know when talking about moment of inertia. So important law to not to master when it is concerned about moment of inertia. The first law here that will help you to solve question under moment of inertia is the conservation of energy. Conservation of energy. Exactly. It means that what? Conservation of energy means the potential energy, because here, when a body is rotating, it's okay, potential energy changes to kinetic energy. Exactly. So the potential energy loss here should be equal to the kinetic energy gain. So that is what you should retain. Potential energy loss equals to kinetic energy gain. I will apply it on when we do one example. You will see. Now, and also note that when I talk about kinetic energy here, we know that kinetic energy of a body moving is half mv squared. But this v is for a body moving what? In a linear route, or let's say what? A body undergoing a linear motion. But here our body, here we are talking about moment of inertia, so surely our body will undergo what? Rotational motion. So I should express this v, which is a linear velocity, in terms of the angular velocity. And v in terms of angular velocity is what? R omega, where omega is what? Omega or w here is the angular velocity. So it's the same as r, and angular velocity is what we call theta dot, the same as r theta dot. So making our half here to be m into r omega square. Now will be half m r square omega. Now m r square, if you remember, m r square is who? Is moment of inertia. So I will have half I, moment of inertia about any axis delta, times omega, or half
moment of inertia about an axis delta theta dot, pardon, here is square, theta dot square, here is square, since this all square here. So that is it. So that is it about kinetic energy. So the kinetic energy for a body undergoing rotational motion, this is it, half moment of inertia about an axis times theta dot square or omega square. It depends on you. So that is the first law you should master, the law of conservation of energy. Now, the next thing you should master here is Newton's second law of motion. Now, for the Newton's second law of motion, Newton's second law of motion. Now, yeah, as I said, the motion is not linear. It is a rotational motion. So when a body is undergoing rotational motion, Newton's second law has two cases. The first case 1, is that the summation of the forces acting on the body should be equal to MA. It's okay. In French, they call it relation dynamique, relation fondamentale de la dynamique. It's okay. So the fundamental dynamic relation is that the summation of forces equals to MA, where A has two components. When a body is undergoing a rotational motion, the acceleration has two components, one which is tangential and one which is radial. We should know it. It's okay. And the tangential component is simply equal to what? dV dt. And we all know that V is what? It will be d r omega all over dt. Now, if the radius of the motion, of the circular motion, is constant, if the radius of the path is okay, if the radius of the circular path taken by the body is constant, therefore it means I will have r d omega dt, which is the same as r theta dot dot. So that is all about a tangential. This is when the radius is constant, and most of the time the radius here is constant, it's not varying. Okay, then r radial is r omega, as simple as that. So it is r theta dot. So that is r radial. So that is it. Now, the second case when we are doing Newton's second law, the second case of Newton's second law is that what? The sum of the moment of external forces acting on the system, the sum of the moment of external force acting on the system is equal to the moment of inertia about the axis of rotation times theta dot dot. That is it. You should also master this one. Now, normally, let me explain this formula very quickly. Normally, when we are talking about, let me consider, because to explain this, let me consider a body rotating. Let me consider a body rotating. Let me consider a body undergoing a circular path like this. Let me do it here. So the body rotating is having, let's say this is the weight. This is the tangential component of the weight. This is the normal component. So let's say this is the tangential component of the weight. Okay. Then let's say this is the body here. This is the angle. The angle here may be theta, or this is the body place may be at point M. Okay. When the body is undergoing, this is it. When the body is performing a circular motion describing this path, you see that what? The weight is having two components, one which is tangential and one which is radial. Is okay. Now, if point O here is my point of pivot, is okay. If I want to calculate the moment, the only force acting on the body here is the weight of the body. So the only moment here, the only external forces having the moment here is the weight. Now there's one weight which is parallel and one weight which is perpendicular. It's okay. So you can see that what? Between these two, between the way which is parallel and the way which is perpendicular, which one is having what? A perpendicular distance from the pivot. This is the pivot, this is the line of the pivot. So it's this one, is the parallel one which is having a perpendicular distance from the pivot. Are you seeing? Is this one? Is the tangential one which is having a perpendicular distance from the pivot. It means that this formula now is simply equals to what? I can simply reduce it as what? As the weight which is parallel or which is tangential times the perpendicular distance separating the two. Let's say surely is the radius times the radius should be equal to what? The moment of inertia about that point of pivot or times who? Theta dot dot. Why am I saying times theta dot dot? Let me explain. We all know that what? Moment of inertia is force times perpendicular distance from the pivot. So force times distance. Are we together? Okay. Now another force is what? Force is mass times acceleration times distance. Let's call that distance r, because surely that distance should be what? The radius of the circular path. So let's call that distance r. Now acceleration, which acceleration is having a moment here? I told that what? It is this one, the tangential acceleration. Is okay, because the normal acceleration or the radial acceleration is along the line of pivot. So the radial acceleration is having no moment. This acceleration is not having a moment. The acceleration which is having a moment is that tangential acceleration, because what? Because the force, the tangential force, is having a perpendicular distance from the pivot. So this acceleration, directly I put what? Tangential, because I told you that what? A body undergoing a rotational motion has two acceleration, tangential and radial. So directly I will consider what? The tangential acceleration. Now another tangential acceleration is given as what? R theta dot dot. This is here. So I'll come and replace it. I'll have mass R theta dot dot times R. So therefore I'll have what? I'll have mass R squared theta dot dot. Mass R squared is what? Moment of inertia theta dot dot. So this is how this formula is being explained. So this is explanation why I'm having the moment of inertia about the center times theta dot dot. This is it. As simple as that. So you people should cram it. So anytime you are answering a question under moment of inertia, when you want to apply Newton's second law, it depends. You can apply case 1, it depends on the question. You can also apply case 2, it depends on the question. Case 2 is it. You should master it. The sum of the moment of external forces equals to the moment of inertia about any axis of rotation times theta dot dot. It will help you. Okay, so I think that is all about the summary. That is all about moment of inertia. Those are the importance. I really summarize the notes. So those are the important things you should know. Now we can now proceed with an example, a sample DC equation, to exercise ourselves. Okay, so let us start with a sample DC equation example. Sample GCE equations. Okay, the first sample DC equation here is I think it's further math mechanics of last year. A uniform circular disc of mass m and radius a performs small oscillations about a smooth horizontal axis in a plane of the disc, which is of a distance x from the diameter of the disc, where x is between 0 and a. Roman 1, show that the least period of oscillation is 2 pi square root of a all over g. Roman 1, we are asked to show that the least period can be written as 2 pi square root of a on g. A on g, okay, that is for how many marks? 8 marks. Okay, students. Very easy, nothing to fear on this question. Now, what you should know is that the period of for every solid oscillating or undergoing a circular motion, it is characterized by a certain period, is okay. And the general formula for a period of oscillation of any body normally is it is 2 pi square root of moment of inertia about the axis of rotation all over mgh. It means all over potential energy. So you can also cram it like this: 2 pi square root of moment of inertia about the axis all over potential energy. Now, normally this is the general formula of period of oscillation of a solid body oscillating. Now the period that you people know, this one, t equals to 2 pi square root of L on G. So what you people know, t equals to 2 pi square root of L on G. what is inside the formula booklet, this is what you people know, but normally it's coming from this general formula. Is okay. Now let me explain how I can live from here to here rapidly without wasting time. This is a period of oscillation of a I think it's for a string mass system. Is okay. So I'm having maybe a string here, then a mass here, and the mass is considered as a point mass. Is okay. It's not considered as a solid. So the mass here is considered as a point mass, and the string or the rod which is being used here is considered what? Is considered to is and the mass of that rod is negligible, and the distance from the point mass, this is the axis of rotation delta, is maybe let us call it that distance L. Is okay. You see that what? For this system, a mass and a string system, for that is for a simple pendulum. The period here will be simply equal to what? There's 2 pi square root of moment of inertia about delta all over mgh. Now the moment of inertia about the system, the moment of inertia of the system is okay, of the system, the string and the mass system about the axis delta is simply what? I tell you that this one is not having a mass. The string is having a negligible mass. It means that the mass is only coming from who? From this m, and let's call that mass m. The mass is only coming from the point mass. Is okay. Then I will calculate. I told you that what? When I consider a point mass, when I want to calculate the moment of inertia of that point mass about the axis of rotation, I take directly what? That mass, then I times the distance separating the point mass and the axis of rotation, which is what? L, then I square it. There is a moment of inertia of the system. Then here, h now here, I told you that h is what? H is the distance. H is the distance from the center of mass, from the center of mass of the system, from the center of mass of the system to the axis of rotation. Now here, the center of mass of the system, where is it? The center of mass of the system is where there is the point mass, because it's the only the string is not having a mass. So the only thing having a mass there is what? The point mass. So that center of mass of the system is here, and then the distance separating the center of mass to the pivot is simply what? L. So while replacing, I'll have 2 pi square root of m L square all over m g h. Square root m cancel no, h here now is L, I replace L cancel one time, I'll have what? L all over g, 2 pi. As simple as that. We come back to what you people know. Is okay. Okay. Then let us, that was a small recall to show you how I can live from the general formula of periods of oscillation of a system to what you know inside the formula booklet. As I said, now here I want to prove that the period of oscillation of that they were talking about what? A disc. Yeah, the period of oscillation of the disc, the least period can be given as this. Now, let me first of all try to represent the disc. If I'm having a disc like this, is okay. A disc performs an oscillation about a smooth horizontal axis in the plane of the disc. When I'm talking about plane, the plane here is what? Is my board. So it means that they are on the same plane, same board. Okay. Plane disc, which is of a distance exactly. It means that if this is the center of the disc, let's say the line passing through the center of the disc, this is it now. Then they are saying that the disc is rotating about its horizontal axis. It's performs small oscillation about a smooth horizontal axis in the plane of the disc, which is of a distance. Okay, the distance where the horizontal axis is at a distance x from the diameter of the disc. If this is the center, this line is the diameter of the disc. It means that that distance should be somewhere here. It means that the axis of rotation of the disc should be somewhere here, making the distance separating the diameter and that horizontal axis should be x. Now the precise that x is greater than 0 smaller than a means that that axis should be inside the disc. I hope you understand it, because x should be greater than 0 smaller than a, knowing that what? The radius the radius is the distance from the center to the circumference is a, means that that horizontal axis should be inside the disc. So this is the axis of rotation. As you can see, this is the axis of rotation of the disc. Is okay. So the first thing to go and calculate is the moment of inertia of what? Of the disc about the axis of rotation delta. So are you seeing that? I will use parallel axis theorem here because I don't want the moment of inertia of the disc about its center, no. I want the moment of inertia of the disc about an axis passing through, about an axis delta. So I'll apply a moment of inertia theory, says I'll first of all calculate the moment of inertia about the axis passing through the center, plus the mass of the disc. The mass of the disc is how many? The mass of the disc is m. Then the distance separating the two parallel axes, that is the axis passing through the center and the axis of rotation, is what? X. Then I square it. As simple as that. Then the moment of inertia of the disc about the center, they gave it. They said that you may assume that the moment of inertia of the disc about its diameter is 1/4 ma square. So I will come here directly. I will put what? I will put 1/4 ma square plus mx square. So there is a moment of inertia of the disc about the axis of rotation delta. As simple as that. Now h, I'm having already the moment of inertia. I'm having this. Now h will be what? H is, I told you that h is the distance from the center of mass. Please understand. H is the distance from the center of mass of the system to the axis of rotation. The center of mass, we wonder what the center of mass of a disc should be at the center. The mass will be mostly concentrated at the center of the disc. Then from that center of mass to the axis of rotation is x, so that distance is x. So making my t, my period, to be 2 pi square root of 1/4 m a square plus m x square divided by m g x. Exactly. So that is it. So this is the expression of the period of rotation of the disc about the axis delta. Then the next question, we are asked to calculate the least period. It means that we want the least period, the least value of this. Is okay. Now, as you can see, t depends on what? 2 pi is a constant, a is a constant, a is a radius, is a constant. So it depends mainly on this x. Is okay. Let me write it like this. I'll have 2 pi square root factorial m. LCM here will give me ma square plus mx here 4 ms square all over 4, then divided by mgx. I'll have ma square plus 4 mx square all over 4 mgx. M will cancel here. Okay, so I will stay with 1 all over g in bracket a square plus 4 x squared divided by 4. So that is it. I think, yeah, you can see that what? This period depends mainly on this value, a squared plus 4x squared over 4. It depends mainly on that value. Please, there were x down here. Don't forget the x, okay? It depends mainly on this value. It means that if I want to calculate the least period length, I should calculate the least value that I can obtain here. So you can see that what? This I can let that value to be a function in terms of x. So a squared plus 4x squared divided by 4x. You can also see that this is a function in terms of x. And for me to calculate the least value of this function, we all know that what? I should go and calculate what? The turning point. The least value of this function, this is a function that will be, I think the function turning point, please, because the coefficient of x squared there is positive. So minimum turning point. So that least value is obtained here. So, and to have this minimum turning point, I should differentiate f of x. I equate to 0. I go and look for that x. When I have now that x, I will come and replace here. Will give me that least. Okay, will give me that least period we are asking for. Are we understanding? So to have them to obtain the minimum value of this function, I should differentiate. I equate to 0. I find for x. When I have now x, I come and replace here. I'll have the minimum value of this function. Now I will replace that minimum value here to have the least period of oscillation of the disc. So let us differentiate quickly. Let us differentiate and see. You see that f prime of x here will be what? Now here I can open a bracket. I will have a square all over 4x plus 4 will cancel, plus 4x square all over 4x. 4 cancel here, x cancel here. So I'm integrating a square all over 4x plus x. You see now? A square all over 4x plus x. So integral of this will give me what? This is the same as a square x to the power negative 1 all over 4. It will be the same as negative a square all over 4x square. Yes, I will have negative a square all over 4x square, then plus 1. Then I equal to 0. When I now equal to 0, what am I having? When I equate to 0, I will bring this one here. I will have negative a square all over 4x square simply equals to negative 1. Equals to negative 1. Okay, so I will have a square all over 4x square equals to negative 1. There is negative and negative cancel. So I will have 4x square all over a square equals to 1. I do the reciprocal. So 4x square equals to a square. Therefore, x is simply equals to a square all over 4 square root of that. X is simply equals to what? A all over 2. So that is the least value of x. Now, when I have now x, I come and replace in t. I'll have 2 pi square root of 1 all over g in bracket. Okay, let us replace x by a all over 2. I'll have a square plus 4 into a square, a all over 2, or square into 4 into a all over 2. So t is equal to 2 pi square root of 1 all over g, 1 all over g. Then when I will square here, I will have a all over a square all over 4. 4 will cancel. I'll have a square plus a square divided by, here I will have 2 what? 2a. I think is it now? Yes. Then when I will simplify it again, I will have t equals to 2 pi square root. Then here I will have a square plus a square is 2a square. The a will cancel. I have 2a square all over 2a. A cancel 1 time, 2 cancel. I will come out with a all over g. That is it. As simple as that. This is the proof. Okay. Nothing difficult there, students. So that is it about the Roman 1 of our question. Now Roman 2. The Roman 2, they are asking us to find the length of the equivalent simple pendulum in this case. As simple. Very simple here. Now, for a simple pendulum, I told you that for a simple pendulum, period is simply equals to what? Roman 2. Period of a simple pendulum is 2 pi square root of L on G. Is okay. Then, if I compare this with the least period, which is 2 pi square root of A on G, so comparing the two, you see that the length of that simple pendulum should only take the value A. That is it. The length of the simple pendulum should be A. You have your 2 marks. So that is all about this question. Now let us proceed with another sample DC question. Okay, students, so the next sample DC question, we are having a uniform rod AB of mass 3m and length 4a has a particle of mass 2m attached to the end B. Okay. Roman 1, show that the moment of inertia of the system about an axis 2a, which is perpendicular to the plane of the rod, is 48 ma squared. 3 marks. Okay, so then you see that this is not even difficult. Eh? So the first thing you're supposed to do here, it means that I'm having my rod like this. Then I'm having a mass here. I'm having a mass here at the end of the rod, which is the mass is 2m. It's okay. So it's having a weight of 2 mg here. The rod is AB, A to B. Okay. So the mass is at point B. Then the length of the rod, is 4a. Then the mass of the rod, the weight of the rod at the center, which is the mass of the rod is 3. Here will be 3 mg. Now you are asked to show that the moment of inertia of the system about an axis 2a. So it means that I want to calculate the moment of inertia of the system about the axis passing through a. So student, what am I supposed to do here? The moment of inertia about the axis passing to a, I should first of all calculate. I will first of all calculate the moment of inertia of the root about 1n. So I will first of all calculate the moment of inertia of the root about an a. Then plus the moment of inertia of who? This the mass m about who? About the NA. As simple as that. Is okay. Then the moment of inertia of the root about point A, we calculated it already. We calculated it, the moment of inertia of the root about A. I think it was 4 all over 3 MA square. That is the moment of inertia of a root about the NA. Is okay. So people should cram it to. I don't think that this formula is inside the formula booklet. People should cram it. And please, yeah. Now, in this case, you can see that what? The mass, big M here now, I will replace big M by 3M. Is okay. The mass of the root is 3M. Then the length, yeah. When we were calculating the moment of inertia about the N, the length, our length there was how many? Our length was 2A. But here the length is 4A. So what am I supposed to do here? I will say that what? It means that L now should be equal to, pardon, it means that 2L should be equal to 4A. Then I find the value of L. L is equal to what? 4A all over 2. So L now is how many? 2A. It means that the length that should be placed here now is 2A. So it means that that moment of inertia will be 4 all over 3. How I'm putting big M, I will put 3M. Then how I'm putting A, I will put how many? 2A. All what? Square. So that is the moment of inertia of the root about one of its N. Then plus the moment of inertia of this mass. The mass is considered as a point mass. I told you that what? When I have a point mass, to calculate the moment of inertia of the point mass about the axis delta, here the axis is what? A. I simply take the mass of the point mass M, then the distance from the point mass to the axis of rotation, which is what? Which is 4A, then I square it. As simple as that. So it's what I will do here. I'll have simply 2M 4A square. So by simplifying, you will see that what? 3 here will cancel. I will stay with 4. Then 4 times 4 is how many? 16A square. Pardon, there is M. 16MA square. Plus, here I'll have 4 square. 16 times 2, 32MA square. So that is it, student. Okay. Okay. Now, if I add the 2, will the proof come out? If I add the 2, 16 plus 32, it will give us what? 48MA square. As simple as that. We come out with the Roman 2 of the equation. Roman 2. Find the distance from A. Find the distance from A of the centroid of the system. Find the distance from A of the centroid of the system. It means that what? I want the distance from A to where the center of the system is. I cannot say that that distance is here. That distance is 2A is wrong. Because I'm having how many masses? I'm having 2 masses. It's okay. I'm having this mass here, which is the mass of the root. I know already that the mass of the root is concentrated here. And the mass of the point mass is here. I'm having 2 masses. So to find this, it means that the center of mass of this system about side A will change. It's okay. It will change. So it will be somewhere between these 2. Now to calculate that center of mass, that is math mechanics. With this center of mass already, that was my video. So, and since it is a horizontal distance, it's not a vertical, therefore we talk about x what? X bar. And remember, I told you that x bar is what? The sum from I of xi mi all over the sum from I of what? Mi. Or you can still put it like this as mi xi, multiplication is commutative. So that is it. Now you can see that what? Yeah, mi, I can start with the mass of the root, which is what? 3m. Then the distance separating xi is the coordinate. The coordinate of xi is what? From A. Xi is how many? 2a. Is okay. Then plus, summation means plus. Then plus the mass m. The distance from 2m to A, the coordinate there is how many? 4a. Then divided by what? 3m plus 2m. Now I will have here 6 ME, is it not? Yes, plus 8 ME divided by 5 M. I think it's making sense now. Yeah. Then here I'll have 6 plus 8 is 14 ME divided by 5 M. M cancel, so it is 14 all over 5 A. So that is the eccentroid, is okay, or the center of mass of our system from the axis A. As simple as that. That was for 2 marks, nothing to fear there. Then let us proceed with the next question. The root, let me put it here, I think that we will use it. It means that our x bar here is simply 14 all over 5 A. Okay, then they are saying the root is smoothly hinged about a horizontal axis 2A and then release from rest. Smoothly hinged about a horizontal axis 2A means that this is the root. Is okay. So this is the root. We smoothly hinge it about A. So this point A here, we hinge it about a horizontal axis like this. Then from that equilibrium position now, we leave it to rotate. We release it. Immediately I will release it. It's like I'm having something like this. Immediately I release it. This is it. Immediately I release it, start what? Rotating. So immediately I will release it. It will rotate and we will form another position here. Let me draw the position. It will form another position here like this, where this is still A, and we make an angle of what? Theta with the horizontal. So remember that this was the weight. Then our new weight will be somewhere here. Is okay. So that is it. Then they are asking us to, the root is smoothly hinged about horizontal axis A, then release from rest. Show that when the root makes an angle of theta with the horizontal, okay. We are asked to show that when the root makes an angle of theta with the horizontal, 12A d theta dt square should give us 7G sine theta. Okay, as I said, the important recall I gave you is that when the laws that you are supposed to know, one of it was the law of conservation of energy. Is okay. For this body to rotate, you see that what? At the horizontal position, the body possesses what? Potential energy. Immediately I leave it, the potential energy changes to what? Kinetic energy. So it means that the loss in the potential energy from this position to the gain of potential energy from the other position, from the rest position, he's losing energy from this position and gaining kinetic energy to this position. Are we understanding? Okay. So this is the law I will apply here to come up with a proof. And then from there, another one, potential energy is simply what? mgh should be equal to what? Kinetic energy. I told you that kinetic energy for a body rotating is what? Half moment of inertia about axis of rotation here, which is A, times what? Omega square. And omega square is what? Theta what? Theta dot square. So this is what I'm using. Okay. Then it means that I should go and calculate. It means that I should go and calculate H. What is the value of H here? You people should look very careful. Now look at it is loss in height. It means that what? If I take my reference maybe to be here, the distance from the initial position of the weight of the center of mass, this is the center of mass, the distance from the initial position of the center of mass of the weight of the system to this reference is here. Then the final position is here. Are you seeing? It means that what? The loss in height, that H represents loss in height. The loss in height here should be this distance. So this distance is H. This is the loss in height. It's okay because I will take this height minus this one. I will have the loss in height. If I take my reference to be here down, it's okay. It means that the height has been reduced. Now to calculate this loss is very easy. Look at here, this theta, this is the theta here again. Is okay. And another one, the distance from here to the center of mass is 14 all over what? 5a. It means that this h is simply equal to what? 14 all over 5a. Since h is the opposite side of the angle, it will be 14 all over 5a what? Cos theta. Opposite. When it's opposite, we use cos theta. As simple as that. I have the value of h. Is okay. Then we'll come and replace here. The mass, remember the mass of the system is how many? 5m, because this is 3m plus 2m, 5m g. Then h is what? H is 14 all over 5 a cos theta should be equal to half. Now, moment of inertia, we calculated the moment of inertia. Okay, we calculated the moment of inertia. It was how many? It was 48 ma squared, then theta dot square. I think, yeah, the moment of inertia was 48 ma squared. So let us see how the proof will come out. This 5 here, we cancel here. Okay. M here, we cancel here. I will stay with 14a cos theta. Why am I having cos theta? Inside the proof, it is sine theta. Please, opposite side. Please, opposite we use sine theta, not cos. H here is the opposite side of the angle, therefore it is sine. So, opposite of our hypotenuse. So, here is sine. I'm very sorry for that. So, here is sine theta. So, when you are solving, please look at your proof so that you should know if you did an error or not. So, here is sine. So, you should have time to correct the error very quickly. So, I realized that the proof was not having cos. It means that I did an error, then I corrected it. Okay, so 14a sine theta should be equal to half here. 2 cancel here 1. 2 cancel 48 how many times? I think here is 2 times and here is 4 times. So I'll have 24a square theta dot square. A here cancel here 1 time. Now what is common here? I think 2 is common now. Yes, 2 is common. Pardon, there was j here. 2 here cancel here 7 times. 2 here cancel here how many times? 12 times. So I'll have 7j sine theta equals to 12a theta dot square. I think that is the proof, right? Yeah, that is the proof. Remember that this a cancel here 1 time. So therefore, let me write it. 12a theta dot square is the same as d theta all over dt all square should be simply equal to how many? 7g sine theta. So that is a proof, as simple as that. You see that there is nothing there, student. There is nothing to fear there. And it was 5 marks. Okay. Okay, students. So that will be all about our lesson of today. But I will do more tutorials. Okay. This is part 1 of our video. I will do more tutorials on part 2 of the video. So stay focused and please subscribe so that you should not miss the upcoming video part 2 of moment of inertia. I think I will do the other June 2021, 22. If I have time, 21, 22, even 20, why not? 22, 21, 20. It's okay, so we are together.